Okay, so the last section of this chapter. We've talked about parallelograms, it seems like forever now, haven't we? When we did section 6.2, 6.3, 6.4, 6.5, all of those sections had to do with parallelograms. Well, this chapter, or this section, I keep saying chapter, this section right here is not about a parallelogram. It's about a figure that has a little bit of similarity to a parallelogram, but it's not one. So there's the picture right there. Make it a little thicker. There we go. All right, that thing right there is what we're talking about today. And it is not a parallelogram, but it does have one similarity to a parallelogram. What does it look like? Why do you think this thing is different than a parallelogram? Or I should say this. Let me start over. What is similar to this and a parallelogram? Ivy, what do you see? What? I can't hear. Okay, 4 sides. Okay, that's a pretty obvious one. Something a little more specific, Jada. What is it? Yeah, I do have a pair of parallel sides, don't I? Okay, so that's kind of close to a parallelogram. But to be a parallelogram, what does it have to do? Not just have one pair of parallel sides, but what? To be a parallelogram? 2, right. Both pairs of opposite sides have to be parallel to each other, don't they? All right. This one, it's kind of obvious that this side right here, this left side and right side, are not parallel. Would you agree with that? Yeah. Now, I know what I just got done talking about in that homework was, don't just trust the picture and all that kind of stuff. But for this problem, yeah, just look at it and say, look, that's going to keep going this way. This is going to go eventually they're going to hit each other, aren't they? All right. But these two won't. These two will keep going completely parallel to each other, which means they're never going to touch. But these two will. So that's basically the definition of this thing. And this thing is called a trapezoid. Have you ever heard of a trapezoid? You've probably heard of it, but you maybe didn't know much about a trapezoid. Maybe you knew what the shape looked like, but you didn't know a whole lot about a trapezoid. So what is it? It's a quadrilateral, okay, where we'll just start off with this, where you have exactly one pair of parallel sides. So it's a quadrilateral, 4-sided figure, all right, that has exactly one pair of parallel sides. When I say exactly, it means no more than that. So a parallelogram does not fit this definition, does it? Because a parallelogram, both pairs of opposite sides are parallel. This one right here, exactly one pair of sides are parallel. Exactly one. That means the other ones cannot be. Got it? Okay. Let's go through a little vocab here, and let's just name some things. Do you see the two sides that are parallel? We call those the bases of the trapezoid. So that's one base, and this is another base. And you're going to find out there's a few similarities between a trapezoid and a triangle. They both start with TR, right? Triangle and trapezoid. There's a couple similarities. A triangle has a base, right? We've talked about that before. A triangle also has what else? So you got a base, and they also have legs to a triangle, don't you? So same thing with a trapezoid. So the non-parallel sides are called the legs. All right, so you couldn't call the two parallel sides the legs. You call the two parallel sides the bases. Everybody with me on that? So the bases are the parallel sides. The legs are the non-parallel sides. You also have these things right here. Let's label this A, B, C, D so I can refer to them. Look at these angles A and B. Look, A connects, sorry, this side right here, this leg connects to this base AB, doesn't it? And this side over here, this leg over here on the right, connects with this base. I'm going to put 2 arcs because they're not necessarily equal to each other. But look, would you agree? They both have this side right here, this top side in common. So we call these two angles base angles. So angle A and angle B are called base angles because they connect the same base together. Do you see any other base angles here? Any other angles that connect the same base? Yeah, D and C. Everybody see that? So D and C. So I'm going to put 3 arcs here and 4 arcs here. So D and C are also, so I'll write that down, angle D and angle C are also base angles. And that just comes in handy because of the definition that we're going to talk about, or some theorem that we're going to talk about in a few minutes here. All right, so A and B are base angles, D and C are base angles. Not the biggest deal in the world, but again, it's just vocab, so we know if I say, well, the base angles are whatever, you know what I'm talking about as far as the base angles. Could I consider A and D to be base angles? No, because A touches this base up here on the top, D touches this base down here on the bottom, okay? So they don't have the bases in common. Okay, it's only the angles that have the bases in common are called base angles. We good with that? All right. Enough of that. So that's a little vocab about a trapezoid. There's something else about a trapezoid we'll talk about in a couple minutes, but let's get to another type of trapezoid. Let's go to a more specific, special type of trapezoid. Okay, that one's not that special. All right, sorry, trapezoid, you're not very special. But this one is a little bit more special. And I'm just going to make this a little bit bigger so we can mess around with it a little bit. Look at this. Every time I look at this, I don't know if this really bugs me a little bit. Let me try something here. I don't know. I thought when I made this thing originally, probably made it last year, I guess. I thought I made it so these two sides were equal. And let's do this. Sorry, this is just because this just bugs me a little bit. And I know it shouldn't, but let's see if this does match up. Yep, that's pretty good, isn't it? I don't know, for some reason my eyes are fooling me. But yeah, those two sides are exactly the same. Do you see what I did? I traced this, right? I copied it, I pasted it, and then I just rotated it a little bit. And yeah, so they are exactly equal to each other. So for some reason my eyes are playing tricks on me, I guess. Anyway, so that's all I wanted to check to see what happens. So look what happens. We have a side here and a side here equal. Remember I said there are some similarities between triangles and trapezoids. Triangle has a base and legs, right? A trapezoid has base and legs. Trapezoid starts with a TR, triangle starts with a TR. Okay, but there's more to the similarity than just that. Look at this. When you have a triangle with two equal sides, what did we call that special triangle when it had two equal sides? Isosceles triangle. Very good. So guess what we're going to call this trapezoid if it has two equal sides? Isosceles trapezoid. Okay, not just sides but legs. Okay, when they have equal legs, when the two legs are equal to each other, here's your parallel sides up top and bottom. When the two legs are equal to each other, we call this an isosceles trapezoid. Isosceles trapezoid. And there's a couple things that we can figure out if we have an isosceles trapezoid. Now remember, the two bases are not going to equal each other. If they did equal each other, well, yeah, if they equaled each other, we'd probably have a parallelogram if they actually equaled each other. Okay, it wouldn't be a trapezoid. All right, so this is an isosceles trapezoid when the two legs are equal to each other. Now, here's something that we know about a isosceles trapezoid. Oh, you know what? Sorry, I should have done this. Let's go back to this real quick. All right, almost forgot. What if I did? This is going to have to do with an isosceles trapezoid, but I wanted to do this first. What did I just draw right there? I just drew two what? What's the word? Diagonals. Diagonals, okay? Does it look like these two diagonals are exactly the same? No, it's not. Okay, if I took this and rotated and flipped it, this one looks quite a bit shorter, doesn't it? DB than AC does. Wouldn't you agree with that? Yeah, I think so. And, you know, if you didn't trust me, I mean, I could copy, paste, you know, put them next to this one, and you'd find out that AC definitely was bigger than BD. All right, but what if we did that to an isosceles trapezoid? Watch this. So what if I drew the diagonals of an isosceles trapezoid? What do you think might be true about those two diagonals there? They are the same, exactly right. Let's call this WXYZ just to be different. So I could say, if this is an isosceles trapezoid, then YW equals KZ. All right? Everybody with me? So the diagonals of an isosceles trapezoid are equal. In fact, let's write that down so we don't forget it. So the diagonals of an isosceles trapezoid, I'll just shorten trapezoid to trap. Is that okay? The diagonals of an isosceles trapezoid are equal. Or you could say congruent. All right, so that's kind of interesting. Do they bisect each other like they do in a parallelogram? No, they don't. Okay, because if they bisect each other, that would make this a parallel. So they don't bisect each other. Does that? It's kind of obvious by looking at the picture, isn't it? Because look at this. We'll put a P right here for point. Watch. Look at PK and PZ. Do they look equal to each other? Nah. PK looks shorter than PZ, doesn't it? So they don't bisect each other. That only works with parallelograms. So don't think that. Okay, but they are equal to each other in length. WY and KZ are equal to each other in length. All right. So let's get rid of this for right now. That's enough of the diagonals. Let's look at something else that might be true. Look at the base angles. Look at the base angles. So what are the base angles? W what? W and X. You see that? So what does it look like this time is true about those base angles? Ethan, you see it? What does it look like? Just off the top of your head, what do you think might be true about W and X? What's that? Yeah. They're not equal to Z and Y. No, just the angles. Just W, X to each other. They're equal to each other, right? Yeah. Look. That's not obvious to you? Again, I hate to say just go by the looks of it, but I'm telling you right now, I'm asking you just about the looks of it. Look at W and look at X. They look like the same exact angle, don't they? And they are. Okay? There are proofs for this, and we could prove that that's true. But for right now, we're just trying to skim through this a little bit. So just take my word for it that those are equal to each other. What about the other base angles? What are the other two base angles? Z and Y. And they probably look what? Equal to each other. And they are. And we have a theorem that says that they are equal to each other. Okay? What do you think might be true about W and Z? They're supplementary. Good, because you look, you got parallel lines cut by transversal. There are consecutive interior angles. Remember that stuff? And consecutive interior angles are supplementary. So W and Z are supplementary. Very good. So what can we say about the base angles? Let's write this down. So what did we say about the base angles? The base angles of an isosceles trapezoid. I'm shorthanding a lot of stuff. So the base angles of an isosceles trapezoid are equal or congruent. All right, so WK. So watch this. What if I said this was, let's say, 50 degrees right here? That's the only thing I told you. I told you it was an isosceles trapezoid, so it's not the only thing I told you. But I told you it was an isosceles trapezoid, and I told you that angle right there. Would you be able to find the other three angles? What's the easiest one to find? Y. Y is the easiest one to find. What would that be? 50, right? Because the base angles are equal. What would the next one be to find? Yeah, W and Z. What's the relationship between W and Z? We just talked about it just a minute ago. They're supplementary, aren't they? So if this is 50, what's this got to be up here? 130. How do we get 130? 180 minus 50. Good, since they're supplementary. If this is 130 without any math at all, what's this one over here going to be? It's got to be 130. You with me on that? Okay. Now, you know what they're going to do eventually, don't you? They're going to make this like 3x plus 2, 5x minus 1, or whatever, right? They'll put x's in there, and you set them equal to each other, solve for x, blah, blah, blah. We've done that tons and tons and tons of times this year, and that's the kind of stuff they're going to do. What if they gave you W and Z? What would you do? You wouldn't set them equal to each other. You would add them up and set them equal to 180. Okay? You getting the hang of this? I just made it real easy. Just stuck a regular number in here. But they're going to put x's in here, and you have to know what to do with them. If they gave you this one and this one, you'd set them equal. If they gave you this one and this one, you'd add them up and set them equal to 180. What does it look like it's true about the opposite angles? What do they look like? Looks like they're supplementary as well, doesn't it? All right, so you could always do that as well. Okay? So there's a few little extra things that you know about an isosceles trapezoid. And I think that's everything on Isosceles Trapezoid, I believe. But there is one more thing we need to talk about. I think we'll be finished. How about that? Let's go back to this regular trapezoid. I just want to show you what we're going to do now isn't just true about an isosceles trapezoid, it's true about any trapezoid. Watch what I'm going to do. I'm going to take this trapezoid right here, and I'm going to take this leg. Remember, the leg is the non-parallel one. And I'm going to find the midpoint of that leg. All right, so I just clicked on it, puts a little dot there right in the middle. So I just kind of slide over to about right there. That looks like the midpoint of that side, doesn't it? Everybody with me? So what do you think I'm going to do to the other side? Find the midpoint of that side. That looks in the middle. That's about right there. Okay, so that would be the midpoint of that side. Guess what I'm going to do to those two midpoints? Take a wild guess. Good idea. I'm going to draw a line that connects those two midpoints. All right, so we start here, and that was close. That's pretty close. All right, so there it is. I connected those two midpoints to each other. Just to show that it's a midpoint, I'm going to put a little tick mark here, put one here, and one here. Everybody with me? Now, this is a segment that's the midpoint of the two sides of the two legs of this trapezoid. So we call this thing right here, we call this the mid segment. Not much of a stretch, is it? Because it's the segment that's in the what? Middle, right? Connects the midpoints. So there's your mid and there's your segment. We call this the mid segment of the trapezoid. You say, okay, big deal, who cares? Well, it is a kind of a big deal because there's a couple things that are true about this. The first thing that's true, remember, this is a trapezoid, so that side and that side have to be parallel, correct? What does it look like just to your eye? Just by looking at it, what do you think might be true about this red line compared to the top and bottom two lines? Looks like it's parallel as well, doesn't it? Doesn't it look like it's going in the same exact direction? And it absolutely is. As long as you connect the midpoints, this is going to be parallel to this, okay? So the mid segment, let's write this down. The mid segment is parallel, just use the symbol, to the what? Of the trapezoid, the bases, right? And we'll put bases because it's parallel to both of these, isn't it? So all three of those lines right there are parallel to each other. And how did we get it parallel? We just connected the midpoints. That's all we did. Now here's the real cool thing. Watch this. The second part of this is pretty interesting. The mid segment, I'll write it down again. So the mid segment. Now what if we put some numbers in here? Let's just make up some numbers. I'm going to do different numbers than we did in the other class. Let's say this is 3, and this is, let's say, 9. Look at this mid segment right here. There's actually a relation to it. You're exactly right. It's actually the average of the two bases. And how do you find the average of something? Add them up and divide by, in this case, you only had 2 of them, so you divide by 2, right? So that right there is what? 3 plus 9 is 12, divided by 2 is 6. So this mid segment right here, it's going to be 6. All right, so what can we say? The mid segment. Now they don't say this in the book. They go through this long explanation of it. Yeah, they say its measure is 1/2 the sum of the lengths of the bases. All right, does that make sense to you? Well, if you said it real slow and you took each word apart, yeah, it might make a little sense. But let's just say it like this: the mid segment is the what of the two bases? It's the average, isn't it? It's the average of the two bases. I think that's an easy way to remember it. But you have to know how to find the average, right? And everybody, I think all of you know how to do that already. Just add them up, divide by 2. Now what if they did this? Now we're going to get a little trickier here. All right, everybody paying attention? What if they didn't tell you? Now, I know you just saw that number, right? All right, so it's not like this is a big surprise to you. But let's just pretend you didn't know what that number was. And we'll call this x. But they told you the mid segment, and they told you one of the other bases, and you have to find the other base, okay? They told you one base, a mid segment, you got to find the other base. Now, what would the math be in order to do that? Well, you could do average again. Now, how would you find the average of the top and the bottom? You would do what? You would go x plus what? 9 do what? Divide it by 2, and that should equal the mid-segment, correct? But this time I know the mid-segment, so I set it equal to 6. I just want to show you how the algebra works out, and then we'll learn a little bit of a shorter, nicer way, okay? So what's the math? What would we do? How do I get x by itself? What do I get rid of first? Yeah, I would multiply by 2 first. Multiply this by 2, multiply this by 2. That cancels out. I've got x plus 9 equals 12. And then subtract 9 from both sides, and we get what we thought we should get, right? We get 3, and so x is going to equal 3. That was an okay way to do it. That's fine. But let's think. If they tell you the mid-segment and one of the bases and you're asked for the other base, let's just do it completely opposite. What did we do the first time? We added together, we divided by 2, didn't we? Well, what's the complete opposite of that? Well, let's go the complete opposite, even the order that you do things in. So instead of add and divide by 2, what do you think we do? We multiply by 2 and then subtract. You follow me on that? That's completely opposite, isn't it? Opposite order and everything. So instead of add together, divide by 2, what do? We multiply by 2 and subtract. So what do we multiply by 2? The mid-segment, right? We take that mid-segment. So this is kind of like a little shortcut from this. So you don't have to go through all that algebra. You just take the mid-segment, you multiply it by 2, which is 12, and then what do you do with the other number? You subtract the other number from it. So 12 minus 9 is 3, and that's how you get that number up here. Can you remember that? All right? So how do you find the mid-segment? You just take the average. You add, divide by 2, right? What if they tell you the mid-segment and one of the other bases? You would multiply the mid-segment by 2. Make sure you always multiply the mid-segment by 2. And then you subtract the other number from it. Can you remember that? All right, so that's what you do. Yes, sir. It's not always going to work that way, though. It just happened to on this particular problem. Like if I did another number, watch this. Let's put some other numbers in here just to show you that that doesn't always work. So, I don't know, pick a number. 10, all right? Pick a number that's bigger than 10, like 30, okay? Actually, I don't want to pick 30 because it's going to do what you said it's going to do. Let's say it's 25. We'll go crazy. We'll pick an odd number here, okay? So we'll say 25. What's this mid-segment going to be? Well, do you just go 25 minus 10 like you said earlier? No. Okay, what do? We add them up, which is what? 35, and then what do? Divide by 2. And that's like 17 and a half. Okay, so that's how long that line right there is going to be. So you can't just do the math that you did earlier, right? It just happened to work on that problem because of the numbers, but it's not always going to work. Make sense? Okay. Well, that's it. There's a couple more things on this lesson. We'll hit that tomorrow. I'll give you a worksheet. Just look at the problems that have to do with trapezoids. We're going to talk about kites tomorrow, a kite, and it looks exactly like you think it's going to look, okay? It looks like a kite. And when you see that on the worksheet, don't do those. Just do the ones with trapezoids. Everybody good with that? Okay.